Hi everyone. In this Dabbling with Database, we're going to take a look at some of the advanced queries that we can create in SQL. Let's go ahead and get started. One of the things that SQL allows us to do is combine information from two or more tables based upon the relationship between those tables, which is usually something between a primary key and a foreign key. And one of the most common joins that we're going to create is what we call an inner join or an equijoin, where the relationship between the two tables shows the common condition, and we only show information that shows up on both tables. We've created databases like the following, where we have orders that have to have exactly one customer associated with them, or order lines that have to have exactly one product associated with them, or order lines that have to have exactly one order associated with them. We can take advantage of these primary key, foreign key relationships in the construction of our queries. As an example, could we get information about customers that have placed orders? Not every customer has placed an order, but if a customer has placed an order, we could look up their information in the customer table and associate it with the specific order that they've placed. Let's take a look at the result of this query. When I run this query, we'll get customers that have placed orders. Not all of our customers from the customers table show up in this query. The customers that have placed orders show up, and they may show up more than once if they've placed more than one order. We can see the customer's ID, their last name, their first name, and the order ID that they placed. Sometimes when we create these more complex queries, we use aliases for our tables. So instead of having to type the entire table name, you can type an abbreviation. In this case, customers will be abbreviated with the letter C and orders abbreviated with the letter O. Just makes typing the query a little bit simpler. It is also possible to construct these queries using either the ON clause or the WHERE clause. The result will still be the same. Sometimes the result you want from your database is quite complex. In this particular query, we are combining multiple tables to create an invoice for a specific order number. In this case, I'm pulling information from the customer table, from the order table, from the order details table, and from the products table. You can see a variety of different fields that we're choosing in the select aspect of this query. I'm choosing them from multiple tables, and I'm setting up aliases for those tables. And I am establishing the relationship between primary keys and foreign keys in each of these different tables. Finally, I add a WHERE statement to filter to a specific order ID. What is the result of this query? In this case, we can see that this order was placed by Pilar Ackerman. They live in Bellevue, Washington. The order was placed on the 5th of January in 2007, and it looks like they purchased one Douglas fir for $18.75. and two Fortune rhododendrons for a total of $48, each rhododendron costing $24. And we've calculated that line total. So this query combines information from lots of different aspects of our database and represents the results in one location. We could write the same query with a WHERE statement as opposed to an ON statement and get the same result. Sometimes we don't want an inner join. We actually want to include all of the results from one side or the other side of the join and then show the matching information if it exists. But if it doesn't exist, we just will show empty information. These are called outer joins. Sometimes we want to combine the results of multiple tables or multiple queries and show all the results in one combined area. This is called a union join. Let's take a look at some examples of these types of queries. In this outer join example, we're going to show all of our customers, whether or not they've placed orders. If they've placed orders, we will also display the order ID. But if they haven't, we'll still see that customer. We'll just show no corresponding order data for that specific customer. Let's look at the result. You can see that the query, when run in SQL Server, shows all of our different customers, and at the top of our list, a lot of them have order ID equaling null. These are customers that exist in our database but have not placed an order yet. If I scroll down this list, however, eventually we get to customers that have placed orders. This query shows all of our customers whether or not they've placed orders. If they have placed orders, we'll see an order ID. If they haven't, we'll see a null. This example takes two separate queries and combines them. The first select query is going to pick up all of our customer information and information from our orders and order details table and pick the specific largest quantity that someone has ordered and display it. The second query is going to show each customer's minimum order. And we're going to combine these two things and then sort based upon that final column. Let's see the result in SQL Server. When I run this union query, you can see a variety of results that say smallest quantity, and then you can see one result for Joe Barry that has the largest quantity. There are obviously a lot of ties for the smallest quantity. Lots of people have ordered a quantity of 1, but only one customer has ordered a quantity of 12, which is the largest quantity in this database. Do note when you're creating union queries that the columns that you are displaying in each of the two separate queries have to be identical. So in this case, we have to have customer ID, last name, first name, quantity, and that either largest or smallest quantity in the min-max column in order to display this as one holistic result. What if we have a table that has a unary relationship? Well, we don't actually have this in the CSI database that we've been using, but in an earlier database we created, the employee database, we do have a situation where the employee table refers to itself for managers. If we wanted to display that information, we could use an inner join to combine the information from the table to itself. Let's run this query and see what it looks like. Note that I am running this query against my EMP database. For my select statement, I'm choosing the employee number from the employee table. I'm choosing the employee's first name from the employee table, and I'm giving it an alias of employee. And then I'm choosing the employee's first name from my manager table, which is an alias for the exact same employee table as the employee table. But I'm picking up that manager from that table as a different category. And what I'm doing is I'm setting the boss from the employee table equal to the employee number from the manager table. So I'm really referring to the table and itself with two different aliases. And the result is you can see that each employee has a manager listed next to them. Alice works for herself, but Ned works for Alice. Andrew and Claire work for Ned. Todd works for Alice, Nancy works for Todd, etc., etc., etc. Another thing that we can do with query language is create subqueries, where we create an inner query inside an outer query. Sometimes this is a condition for our where clause, or it's a derived table in the from clause, or it's within the having clause. Sometimes these subqueries are uncorrelated. They could be executed once for the entire outer query. But sometimes they are correlated. You have to run them differently every time you return a result from the outer query. Here's an example of running a query where we're going to pick up the last name and the first name from our customer's table, but our where clause is going to look for customer ID in the result of a second inner query, where we're selecting the customer ID from our orders table. So we're checking to see if the customer ID is in the orders table or not. If it is inside that orders table, then we say that those are the only customer IDs that satisfy the where clause for this query, and then we pick up the last name and first name from the customer table. Let's run this query. This query will give us last name and first name for all of our customers, but only if they've placed orders. For uncorrelated subqueries, they don't depend on information from the outer query, which means you can run them once and then use them for the rest of the outer query. For correlated subqueries, they use information from the outer query, which means every time we calculate a row for the outer query, we then have to run the inner subquery against that result. In this query subquery example, we're selecting individual order IDs from our order details table, and we're checking to see where something exists. And specifically, the subquery is selecting everything from the products table where the product ID is equal to the product ID from our order details table. and I'm filtering that the only category I'm interested in is category ID 3. This subquery is testing for a value that comes from the outer query. So every time the outer query comes up with a distinct order ID, then I check to see if our product ID matches our product ID in an order details table and the category matches 3. So this query has to run the subquery every time it comes up with a result in the outer query. The only orders that fit into category 3 and have that specific product in their order details table are orders that are listed in the following result. This is an interesting way of filtering down to specific orders that included specific products in their order details. The last type of advanced query we'll look at is a derived table example. This one is going to show us all products that have a standard price that is higher than the average price. So first we run a outer query where we're going to select our product name and our unit price and our average price. In the inner query, we're going to select the AVG or average of our unit price and give it an alias, AVG price. And that makes that calculation available to the outer query. You can see that I had to give the derived table an alias, even though I don't actually refer to it. So this would run the inner query and come up with all of our average prices, and then it would make those average prices available for the outer query, which displays our product name, our unit price, and our average price. And finally, we have a where clause that says only show us products where the unit price is higher than that average price we've calculated. When I run this query, it gives us lots of products and their unit price. And you can see that all of the products that are listed have unit prices that are higher than our average price, which is $17.98. I could flip this query and show you all the ones that are less than the average price. And you'd see a completely different list of products that have unit prices that are lower than $7.98. When you are developing queries for your database, it's important that you're very familiar with the data model. You understand all of your different tables and how they relate to one another. You also understand what kind of results you're trying to get out of the database and what sorts of attributes you're trying to display, whether they are columns from your tables or they are calculated results or aggregated results from those tables. You'll know how to identify the entities and the attributes from those various entities, review your entity relationship diagram, construct joins or wheres where necessary, fine-tune your result by using group bys or halvings if necessary, and then think about whether you have unusual data that might cause exceptions to the rule or strange results, and perhaps figure out a way of filtering that information out. Think about writing efficient queries. If you can avoid things like select star, where you pull all of the information from a table, you'll get a query that runs more efficiently. Only select the attributes that you're interested in looking at. Also try to limit the number of subqueries that you write. Subqueries are computationally expensive. Also, if you're using data in many different places, consider making a separate query and store its results, and then you can access the results of that query in other places without having to rewrite that code. In terms of guidelines for better query design, it's important to understand how indexes are used and also how to use things like optimizer statistics. Certainly, if you have the opportunity to change your data types to compatible fields and literals, your queries will run better. When possible, the simpler query is the better choice. And if that means breaking down complicated queries into multiple simple parts and then combining those results, that's fine. It's better to do that than nesting one query inside another, and it's certainly better than combining a query with itself. Certainly, if you can, avoid things like self-joins. Writing better queries sometimes requires temporary tables, sometimes requires you to combine some update operations. You do want to try to limit the information that you retrieve to keep things as efficient and as fast as possible. And don't have databases try to sort information if you don't have an index associated with that data. It will be computationally expensive. That's it for this video. Thanks so much for watching. See you next time.